In this video, we are going to talk about complex eigenvalues. And like the other videos for this chapter, this involves only square matrices. So also, like the invertible matrix theorem, you don't want to apply these concepts to non-square matrices. This is our overview slide, which we will spend 3 or 4 minutes going over before we go through each topic in more detail and more examples. We will start by saying when you have the characteristic equation of an n by n matrix, then you're going to have a polynomial of degree n, which means you will have exactly n roots when you count multiplicities and complex roots. So in the previous video, we only looked at matrices that had real roots. In this video, we will consider the complex roots. So in the previous video, when we had these real eigenvalues, then the eigenvectors ended up to be those vectors that the transformation matrix A only scales and does not rotate. So in other words, we said that if we had an eigenvector associated with a real eigenvalue, then A times x would simply equal to a scalar multiple, which was the eigenvalue times x. This is different from complex eigenvalues, and the complex eigenvectors associated with those eigenvalues may indeed rotate. It may not just be a scalar, but we're getting ahead, so let's back up. The first thing to know about complex eigenvalues is that they occur in conjugate pairs. So if you have lambda equals a plus ib is a eigenvalue, then you also know that lambda equals a minus ib is also an eigenvalue. The conjugate pair is also an eigenvalue. Second, we have this theorem that is going to be really useful. So if A is a real 2 by 2 matrix, so A has real entries, but it has complex eigenvalues, and in particular we're going to look at one complex of the complex eigenvalue, lambda equals a plus ib, where b is not 0, and its associated eigenvector v. So this eigenvector is associated with this eigenvalue in C2. So in other words, it's a vector which might have complex numbers as its components for this vector. Then we can write A as being a matrix similar to a matrix C, where C is of the form a 2 by 2 with column vectors AB and minus BA. So this theorem says that A is going to be similar to the matrix C, and we have the invertible matrix P, where we can find the invertible matrix. Its first column is the real part of the eigenvector V, and its second column vector is the imaginary part of the eigenvector V, and then C is equal to AB minus BA, where A and B come from the eigenvalue. As I had mentioned, the complex eigenvector then may or may not just be a simple lengthening or contraction. It may also have rotation. So the way we're going to analyze the complex eigenvectors is with this matrix C that A is similar to here. And the matrix C then will show that we can make it into a product of a matrix that just involves scaling and a matrix that just involves rotation. In this way, we can analyze the action of C and in turn analyze the action of A. So these are the main ideas that we will be working with. Our first example is one of a matrix with complex eigenvalues and where we can say that the eigenvectors rotate. So just to drive home the point that this is different than when we have eigenvectors associated with real eigenvalues. So our matrix A is the 2 by 2 matrix with real entries. The first column vector is 0, 1, negative 1, 0. We can find then the eigenvalues are plus and minus I. We illustrate that we can find associated eigenvectors with that. And the other point about this matrix is this matrix multiplies every vector. It's a rotation, rotates every vector it multiplies. In fact, this is one of the rotation matrices. When we had talked about A as a transformation, we had certain matrices that rotate, and this is one of them. So not only does it rotate all vectors, specifically, it even rotates our eigenvectors. Our main example of this video is one with complex eigenvalues. It is a 2 by 2 matrix A with real entries, with the first column vector being 0.5, 0.75, and the second column vector being negative 0.6, 1.1. We are going to use this example 1 to illustrate how we find eigenvalues using the characteristic equation. We're going to see how we find the associated eigenvectors by solving the homogeneous equation. Then we're going to find this matrix C that A is similar to. And then once we have C, we're going to break C into a product of two matrices, one responsible for scaling and one responsible for rotating. In this way, we're able to analyze C and in turn analyze A. And last, just to round things out, we will look at some properties of complex conjugates. And now we're ready to go through our topics again in more detail and with more examples. We'll break down the introduction first. So since the characteristic equation of an n by n matrix involves a polynomial of degree n, then the equation always has n roots if we count multiplicities and complex roots. The next thing to know is when there are real eigenvalues, then the eigenvectors that are associated with those eigenvalues are those that the matrix A, when we consider it a transformation, only scales the vector and does not rotate the vector. So we have our familiar eigenvector eigenvalue equation, A times the vector x. If it's an eigenvector, this will equal to a scalar lambda times x. When there are complex eigenvalues, then A is similar to a complex matrix C. And from definition as similar, that means A is equal to P, C, P inverse, where P can be constructed from the real and imaginary parts of the eigenvector of A, and C is constructed from the real and imaginary parts of the eigenvalue of A. This theorem here tells us exactly how the matrix P and C are constructed. So if A is a real 2 by 2 matrix with complex eigenvalue lambda equals A plus IB, where B is not 0, and we have an associated eigenvector V in C2, then A is equal to PC P inverse, where P is the matrix with column vectors, the first column vector being the real part of our eigenvector V, and the second column vector is the imaginary part of the column eigenvector V. And then C is equal to AB minus BA, where A is the real part of the eigenvalue and B is the imaginary part of the eigenvalue. And we're going to discuss C more, but we'll see, no pun intended, that C can be separated and can be factored into a product of two matrices, one which introduces a scaling and two which introduces a rotation. And sort of to summarize some of these things is the complex roots of the characteristic equation provides critical information about A that arise in real-life problems such as real dynamical systems that involve periodic motion, vibration, or some type of rotation in space. Our first example is to drive home the point that eigenvectors associated with complex eigenvalues may rotate, may have a rotation. And we're going to look at this matrix A, the 2 by 2 matrix with column vectors 0, 1, negative 1, 0. You may recognize this as one that we had studied when we talked about matrices as transformations, and some of those transformations were rotations. This was one of them. And in particular, A is a counterclockwise rotation through a quarter turn. So the action of A is periodic, since after 4 quarter turns, a vector is back to where it started. And just to illustrate this rotation through a quarter turn, I multiplied A times my vector 1, 1, and I just arbitrarily chose 1, 1, but I thought it kind of looked nice on the graph. When you multiply A, you see that the result is the vector negative 1, 1, which is over here. So it's a 90-degree rotation, same length. The length remains the same. So here is the action of A. Then after that, I plugged in my resulting vector, my negative 1, 1, back into A, multiplied it by A, and I get the new vector negative 1, 1, and then I plugged in my negative 1, 1 multiplied by A and got my new vector 1, negative 1. Then I plugged in my 1, negative 1 multiplied by A, and I returned back to my 1, 1. Also, these results, when you keep plugging in your result in to find the next vector, those vectors, so like the 1, 1, the negative 1's 1, negative, negative 1, those are called iterates. Since A is purely a rotation, A rotates all vectors. So we expect to have no real eigenvalues, and we can verify that by looking at A's characteristic equation, that is the determinant of A minus lambda I, and we find that lambda is equal to plus or minus I. We can then find eigenvectors associated with these eigenvalues. So we permit A to operate on complex vectors. So we have A, and we found this vector, which I haven't shown you how to find it, they just appeared. So we have this vector 1 minus I, and we can see if when we do the multiplication, that's going to be I1, which is equal to I times 1 minus I, which is just I, our eigenvalue, times our original vector. So we can find these corresponding eigenvectors to go with our eigenvalues. But what you want to keep in mind is that these eigenvectors are rotated by matrix A because matrix A rotates every vector. So this is different from eigenvectors associated with real eigenvalues. Now we are ready to look at our main example for our study of complex eigenvalues. Our main example is the 2 by 2 matrix A with real values. The first column vector is 0.5, 0.75, and the second column vector is negative 0.6, 1.1. The first thing I want to do is find the eigenvalues of A using the characteristic equation. And this should look quite familiar. We start with our eigenvector eigenvalue equation, AX equals lambda x, subtract lambda x from both sides of the equation, and then introduce our I. So I have A minus lambda I, x equals 0. Now I have my matrix A minus lambda I, where I subtract lambda from the diagonal, so I have 0.5 minus lambda, 0.75, and my second column is minus 0.6, 1.1 minus lambda. To get the characteristic equation then, I'm going to take the determinant of A minus lambda I, so I cross multiply my 0.5 minus lambda times 1.1 minus lambda, and then minus my negative 0.6 times 0.75, which is equal to plus 0.45. Doing the algebra, I get lambda squared minus 1.6 lambda plus 1 equals 0, and using the quadratic formula, I get lambda is equal to 0.8 plus or minus 0.6 I. So I have successfully found my eigenvalues, and they are indeed complex. I'm ready to do step 2, which is to find the associated eigenvectors. I'll start with my first eigenvalue as 0.8 minus 0.6 I. So I plug that into my A minus lambda I. So I have my 0.5 minus lambda, lambda being 0.8 minus 0.6 I. And then the next entry in that column vector is 0.75. My next column vector, I start with minus 0.6, and the next entry is 1.1 minus lambda. So 1.1 minus, and my lambda is 0.8 minus 0.6 I. I do the arithmetic to get the 2 by 2 equation with the first column vector equal to minus 0.3 plus 0.6 I, 0.75, and the second column vector equal to minus 0.6, 0.3 plus 0.6 I. Normally what I would do now is I would look at this and I would look for non-trivial solutions X that solves the homogeneous equation. So here would be my augmented matrix, but row reduction with complex numbers is kind of unpleasant. Actually, even with real numbers, it's sort of unpleasant, but this is even more unpleasant. So we're going to look at this matrix and consider it a representation of two linear equations. This is the first equation, this is the second equation. So the first one is the minus 0.3 plus 0.6 I times x1 minus 0.6 x2 equals 0. And my second linear equation is 0.75 x1 plus 0.3 plus 0.6 I x2 equals 0. So here we have two equations, two unknowns, a system of linear equations. And what I can do is I can choose this one here, I could have chosen the first one, but I chose the second one, 0.75 x1 plus 0.3 plus 0.6 I x2 equals 0. And I solve for x1 in terms of x2. So x1 is equal to minus 0.4 minus 0.8 I x2. At this point, I choose a value for x2 and then figure out what x1 is. I often choose the value 1. So often my first impulse would be x2 is equal to 1 because 1 is a small number to plug in. But I wanted to get rid of the decimals. So I certainly could have chosen x2 equals 10. That would have gotten rid of my decimals. But I chose x2 equals 5 because that eliminates the decimals with the smallest, still having the smallest numbers here. So if I choose x2 equals 5, then x1 is going to be equal to minus 2 minus 4i, which means this vector v1 is equal to minus 2 minus 4i, 5. And this is a basis for the eigenvalue eigenvalue 0.08 minus 0.6i. And as I had mentioned, if you chose a different x2, you would have a different vector here. However, your vector should be a multiple of my v1. So I reduced all my work here to give myself a little more space. And the first thing I'm going to say, you can, using a similar method, you can find v2, the second eigenvector, associated with the eigenvalue 0.8 plus 0.6i, so the addition of 0.6i. And you'll find that this is the eigenvector for this eigenvalue. This point, I think it's a good idea to start checking to make sure that the eigenvectors and eigenvalues are what we think they are. So in other words, I can multiply a times my eigenvector, and I chose v2, my second eigenvector, my minus 2 plus 4i, 5. And when I multiply this, I'm going to expect to get the same v2 times a scalar. So I did my multiplication, my row times column, 0.5 times minus 2 plus 4i is minus 1 plus 2i. My minus 0.6 times 5 is minus 3. My 0.75 times my minus 2 plus 4i is minus 1.5 plus 3i. And 1.1 times 5 is 5.5. I do my arithmetic and I get 2i minus 4 plus 3i, which I'm hoping, and I haven't verified this yet, but I'm hoping that this is equal to my eigenvalue, 0.8 plus 0.6i, times my vector v2. So now I have to look at how to confirm this equality here. And instead of trying to mangle this expression until I get this, what I did is I just multiplied these two together and verified it's equal to 2i minus 4 plus 3i. So I have 0.8 plus 0.6i, and I multiplied by the top, minus 2 plus 4i, and I saw that was equal to, and you can look at my arithmetic, or check my arithmetic, but what you will get is minus 4 plus 2i, which is exactly the same, except in a different order. And you can verify the 0.8 plus 0.6i times 5 is equal to 4 plus 3i. Or you can take my word for it. But I have verified that I do have this eigenvalue here, my 0.8 plus 6i, and my eigenvector pair. Here I've summarized the results I have so far for my matrix A. I have my eigenvalues here. I have my two eigenvectors. Before I come to this next step here where I start to analyze the matrix A, I have a couple of things to say about complex conjugates. So the first part is if we have a vector x that has real and imaginary parts, we want to be able to separate it out. We don't denote the real part as RE and the imaginary part as IM, and the imaginary part is the thing that gets multiplied by I. So for example, if we have the vector x is equal to 3 minus I, and 2 plus 5i, then we can rewrite this as the vector 3, 0, 2 plus I times the vector minus 1, 1, and 5. So that means the real part of x is equal to the 3, 0, 2, and the imaginary part of x is minus 1, 1, 5. And again, this is how it fits this equation. We have the real part plus I times the imaginary part will give us x. And we have this complex conjugate, which is much like the complex conjugate in when you did numbers, not vectors. It's the real part minus the imaginary part. So now it's our 3, 0, 2 minus I times the imaginary part, negative 1, 1, 5. So we get 3 plus I, 0 minus I, and 2 minus 5i. That's the complex conjugate of x. And unfortunately, my notation for vector looks a lot like complex conjugate, so I'm going to try to make this arrow more clear. So now I have, if B is an m by n matrix with possible complex entries, this is a matrix now, then the complex conjugate of B, the matrix B, denotes the matrix whose entries are the complex conjugates of the entries of B. And if we let R be a complex number and X be any vector, then the properties of conjugates for complex numbers carry over to complex matrix algebra. So a scalar R times a vector X, the conjugate of that is the conjugate of R times the conjugate of X. The conjugate of the matrix B times X is equal to the conjugate of B times the conjugate of X. And the conjugate of matrix B times C is the conjugate of B times the conjugate of C. And the scalar R times b, the conjugate of the scalar r times b is equal to the conjugate of r times the conjugate of b. Now we are ready to analyze our matrix A by writing A in this form here, where A is similar to a matrix C, where C has the form AB minus BA, and to find C and P, we have used this theorem here. I rearranged my page to show the work we've done so far, and here's our theorem. So A is a real 2 by 2 matrix with complex eigenvalue lambda equals A plus IB, where B is not 0, and the associated eigenvector V in C2. So V is associated with this eigenvalue. Then A is equal to P, C, P inverse, where P is the matrix, where the first column vector is the real portion of the eigenvector V, and the second column vector is the imaginary portion of the eigenvector V, and C equals AB minus BA, where A and B come from the eigenvalue. And these two formulas here for our P and C, I've also copied up here. So here's P and here is C. Applying this now to our example A, I rewrote my matrix A here. I rewrote the first eigenvector we found, the -2 minus 4i5, which was associated with the eigenvector 0.8 minus 0.6i, and then our second eigenvector -2 plus 4i5, associated with the eigenvalue 0.8 plus 0.6i. But now I'm going to find my P matrix, which is the real part of an eigenvector. So I'm going to choose this vector here. So the real part is 2, -5. The second column is going to be the imaginary part of our eigenvector. So that will be -4, 0. And then looking at C, I need to find my eigenvalue. So I have A on the diagonal. That's our real part. So I have 0.8 on our diagonal. And the other, our -b then is going to be our 0.6. And then our B is going to be minus 0.6. Just a note, once I had P, I can derive my matrix C from the equation A equals P, C, P inverse. I start with A equals P, C, P inverse. I multiply both sides of the equation on the left by P inverse. So I have P inverse A and P inverse my P, C, P inverse. Then I multiply both sides of this equation by P on the right. So I'll have P inverse A, P, and P inverse P, C, P inverse P. Now I could group these two together because multiplication is associative, and I group the P inverse P together. So here I get I, C, I, which is just as equal to C. So this gives me a formula for C is P inverse AP. Of course, that would mean you need to calculate P inverse, which I have written here, and I did the calculation here. I put P and I row reduced it alongside I until P became I, and then what I was becomes P inverse. To be honest, I'm not sure why you would want to do it this way when you can just use this formula here from the theorem, but your book did it this way, so I figured I should just show you what was going on. Now that we have A in this form, P, C, P inverse, where C is this matrix, 2 by 2 matrix with column vectors A, B, and minus BA, we're going to focus on the matrix C. Our goal is to separate matrix C into a product of two matrices, the first which only has a scaling, only scales other vectors, and another matrix which only rotates. Again, here I have my summary of what we've done so far. We found the eigenvalues, we find the eigenvectors, we wrote A as a similar matrix to C, C in this form, AB minus BA. So we're going to look now at C, this matrix C, and we're going to try to find it as a product of a scaling matrix and a rotation matrix. And what we're going to say about C now applies to any matrix that has this form. It's a 2 by 2 with column vectors A, B minus BA. It doesn't matter how we got this matrix. It doesn't have to come through these eigenvalues and eigenvectors. What we're saying now is true of any matrix C of this form. Looking at C using our eigenvector equation, Cx minus lambda x, subtracting lambda x from both sides of the equation, cx minus lambda x equals 0, introducing the I, c minus lambda I x equals 0, then our c minus lambda I matrix subtracts lambda from the diagonal, so our first column vector is c minus lambda b, and our second column vector is minus b a minus lambda. Looking at the determinant then, we get lambda is equal to a plus or minus ib. Now I'm going to look at this eigenvalue, and I'm first going to just take a plus ib as just the positive one. So if I plot this as a complex number, often we use x to plot the real part, so I have a, and y to plot the imaginary part, b. So my complex number then is represented by this point here, a plus ib. The radius here is the distance from the origin, which is the magnitude of lambda, which is square root of a squared plus b squared, and you can see this is just a and b, so using the Pythagorean theorem we have r. And then we also have, using trigonometry, that this distance here, a, is r cosine theta, and this distance here, which is b, is r sine theta. Now I can rewrite my matrix C over here, so it's the column vectors a, b, and minus b, a. I can multiply by r, but then I'm going to have to divide each element of C by r. So I have r times the matrix a divided by r, b divided by r, and the second column vector minus b divided by r, a divided by r. So now I can throw in an I in front of r, because you can always multiply by the identity matrix, which means my r times I is this 2 by 2 matrix, r0, 0, r. And over here, my a divided by r, looking at my trigonometry over here, will be equal to cosine theta. And then my minus b divided by r, again using trigonometry, will be equal to minus sine of theta. And the rest of the matrix then, my b divided by r will be sine of theta, and my a divided by r will be cosine of theta. And what you notice is this here, this R0, 0R matrix is simply scaling. So when you multiply this matrix times a vector x, all you do is scale that vector x. Whereas this matrix here, when you multiply it by a vector x, what you do is you rotate the vector x by the angle theta in the counterclockwise direction. So just a picture, if we have this vector x, when we multiply our matrix C times x, we get this rotation, and we also get some scaling. That's my alarm, by the way. What you want to remember is this product here is dependent on C having this form. So C is a 2 by 2 matrix with the first column vector equal to AB and the second column vector equal to minus BA. Applying this to our example A here, we have our two eigenvectors, we have our matrix P, our matrix C here, and we want to apply the fact that our matrix C, which is in the form AB minus BA, can be then written as a product as a matrix that scales and a matrix that rotates. So what we get with our particular C, which is the 2 by 2 with the first column vector as 0.8, 0.6, and the second column vector is negative 0.6, 0.8, that's equal to, we wanted it in this form here. So R is equal to the square root of 0.8 squared plus 0.6 squared, which is equal to 1, which means here, this scaling matrix simply becomes the identity matrix. So it really doesn't scale anything at all. So first we'll note that C is a pure rotation. And if you look at A is equal to P, C, P inverse. So inside, this is a series of 3 different transformations. Remember, you can think of matrix multiplication as transforming a vector. So here we have 3 transformations that equals A, and this middle transformation is a rotation that happens inside of A. So this completes our main example. I have one more example. This next example is just sort of an illustration of the rotations. So if we have this 3 by 3 matrix A with column vectors 0.8, 0.60, negative 0.6, 0.80, and 0, 0, 1.07, we're given that it has eigenvalues lambda as 0.8 plus or minus 0.6i, and a third eigenvalue, lambda equals 1.07. So we'll note that any vector w naught in the x1, x2 plane or the xy plane, that is with the third coordinate z is equal to 0, is rotated by a into another point in the plane. And I kind of illustrated that just by choosing a point 1, 1, 0. So it's in the xy or x1, x2 plane. And when you multiply this out, you can see why. Here you get, 0.8 minus 0.6, so 0.2. You have 0.6 plus 0.8, 1.4. So it's rotating in the plane, but here you have 0, 0, and then 0. So you stay in the x1, x2 plane, but there's a rotation. So here, for example, if you're at w naught, when you multiply times this matrix A, you get to w1, but you're still in the plane. And then when you multiply w1 by A, you get to w2, and you kind of make the circle in the plane. Any other vector x naught in the plane has its x3 coordinate multiplied by 1.07, and I chose another vector 1, 1, 1 that is not in the x1, x2 plane, and you can see here you get, your 0.8 minus 0.6, you get your 0.6 plus 0.8, and here you have 0, 0, and then you have 1.7. So this factor here, and you could have done this with an x1, x2, 0, and x1, x2, x3, so you could show this in the general case, but I just showed it in a particular case. So here you increase your third term, or you multiply it by 1.7. So in other words, if you have something that looks like w1, except you're at 1, then you'll see that your x naught will get raised. Your x1 is raised a similar amount, and so it kind of circles around as well. So the iterates of the points, the iterates if you calculate w1, w2, etc., x naught, x1 is equal to a times x naught, x2 is equal to a times x1, etc. Of the points 2, 0, 0 and 2, 0, 1 under the multiplication, then the iterates are shown in this graph here. This last topic here we had actually already covered somewhere in the middle. We talked about complex conjugates. I just put it last in my main topic because I didn't want it to interrupt the flow of my main example. At this point, I have one more example for you to try. So since we've covered all the main topics, this last example I suggest after you've heard the problem statement, you pause your video, give the problem a try before you look at the solution. The additional problem is to show if a and b are real numbers, then the eigenvalues of a are a plus bi and a minus bi, with corresponding eigenvectors 1 minus I and 1i, and A is equal to the 2 by 2 matrix with column vectors AB and negative BA. Actually, we had already done part of this problem in a previous example, except we called the matrix C. So I just copied this over. So forgive me, this matrix C is equal to matrix A. So C is equal to the 2 by 2 with column vectors AB minus BA, where A and B are real and A and B are not both 0. We did our eigenvector equation. Cx equals a scalar multiple of x. Subtracting lambda x from both sides of the equation, we get Cx minus lambda x equals 0. And then introducing I, we get C minus lambda I x equals 0. I keep saying this equation because I'm hoping you'll remember it. And so if we look at C minus lambda I, that would be that gives us the minus lambda across the diagonal. So we have A minus lambda B, and then minus B, A minus lambda. Looking at the determinant of this, cross-multiplying, we get A minus lambda squared plus B squared, which gives us lambda squared minus 2A lambda plus A squared plus B squared equals, and setting that equal to 0, we use our quadratic formula, and we get lambda equals A plus or minus IB. Looking at our first eigenvalue, lambda equals A plus IB, so we can find the corresponding eigenvector. We're going to plug lambda into C minus lambda I. So we have A minus lambda, so A minus A plus IB, and then we have B. Our second column vector is negative B and A minus lambda, so negative B, A minus A plus IB, and then we're setting this C minus I, lambda I equal to 0, so the augmented matrix has 0. When I first I did the subtraction, so A minus A, so I'm left with minus IB, B, and then minus B, and minus IB, 0, 0. I row reduce until I get this matrix. So what I have is minus I B x1 equals B x2. In other words, minus I x1 equals x2. So I can set x1 equal to 1, and that will make x2 equal to negative I. So this is my eigenvector for lambda equals A plus IB. Doing a similar thing for our second eigenvector, A lambda equals A minus IB. I plug in the lambda into the C minus lambda I, and I get the 2 by 2 matrix over here. With the first column vector is A minus lambda, which is A minus IB, and then B. My second column vector is minus B, and then A minus lambda, which is A minus IB, and then we also put in our 0, 0 to give us our augmented matrix for the homogeneous equation, subtracting A minus A, so I'm left with plus IB, B, and then minus B, IB, 0, 0. Row reducing, I get I x1 equals x2, so I'm going to let x1 again equal to 1. That means x2 is equal to I. So 1I is my eigenvector associated with lambda equals A minus IB. And then I'm done. To review what we have covered in this video, so we talked about complex eigenvalues, and it's different from real eigenvalues, where we know that if we have an eigenvector associated with a real eigenvalue, then A times that eigenvector x is simply a scalar multiple, the eigenvalue times the vector x. So for complex eigenvalues, the eigenvectors, this is not true. The first thing that we should talk about, though, for complex eigenvalues is that complex eigenvalues occur in conjugate pairs. So if lambda is equal to A plus IB, then you also know that there's another eigenvalue, A minus IB. We have this theorem here that we used that talked about how we can make A a real 2 by 2 matrix with complex eigenvalues, similar to a matrix C, where C is based on the eigenvalues, and this matrix, the invertible matrix P, is based on the eigenvector. We had this quick example here just to, again, reiterate the fact that when we have complex eigenvalues, the eigenvectors may indeed rotate, which is unlike real eigenvectors associated with real eigenvalues. For our main example, this matrix 2 by 2 matrix A with real entries, the first column vector being 0.5, 0.75, and the second column vector being minus 0.6, 1.1. First, we found the eigenvalues using the characteristic equations, and we found two complex eigenvalues, lambda equals 0.86 plus 0.6i, and the second eigenvalue being 0.8 minus 0.6i, again, the conjugate pairs. Next, we found the associated eigenvectors by solving this homogeneous equation, A minus lambda I x equals 0. Once we had the eigenvalue and then one eigenvector, we solved for two, but we only needed one eigenvector then to make A into the form of P times the matrix C times P inverse, where C has the form of a 2 by 2 matrix with column vectors AB minus BA. We used our theorem up here, over here, to find that A is equal to the real part of our eigenvalue, and B is equal to the imaginary part of our eigenvalue. Now that we have A in this form, PC, P inverse, where C is of the form AB minus BA, we can take C and we showed that we can break that up into a product of two matrices, one that is a pure scaling of our vector, and the second is pure rotation of our vector. So by showing C, we can analyze the scaling and the rotation separately, then we can also analyze A, since C is sort of in the middle. These scalings and these rotations happen in the middle of A. And somewhere in the middle of all this, we also talked about properties of complex conjugates. So that's it for this video. Thank you for watching.